Imagine you're on a cosmic highway with a universal speed limit, the speed of light. This isn't just a number, it's the law of the universe. 299,792,458 meters per second. Nothing with mass can reach it, and light itself can never exceed it. This constant, the c in Einstein's EIMC2, shapes the very fabric of reality. When you look at the stars, you're seeing into the past. Proxima Centauri's light took over 4 years to reach us. Andromeda's took millions. The speed of light weaves space-time together, ensuring that no matter how fast you chase it, light always races ahead at the same speed. But light is more than just fast. It's mysterious. Sometimes it acts like a particle, a photon. Other times it's a wave, spreading and interfering. This wave-particle duality is at the heart of quantum mechanics. Light's identity depends on how we observe it, allowing it to perform mind-bending tricks. The universe is built on such contradictions. A particle that's also a wave, a constant speed that can appear to slow down. This duality opens up possibilities that challenge our intuition about time. The sunbeam warming your face is the end of an epic journey, governed by the strangest rules in the cosmos. Light's constancy is what lets us peer into the universe's history. Its dual nature is the key to unlocking the secrets of space and time. As we'll see, these properties let us manipulate light in ways that seem impossible. The story of light is the story of reality itself, stranger than we ever imagined, and it all begins with that unbreakable cosmic speed limit. The speed of light, c, is only absolute in a vacuum. The universe is filled with matter, air, water, glass, even diamonds, and when light passes through, it slows down. This isn't breaking the rules, it's like a runner weaving through a crowd. In water, light's journey is delayed as photons are absorbed and re-emitted by atoms, slowing the overall signal. In air, the slowdown is tiny. In diamond, light crawls at less than half its vacuum speed. This slowing causes refraction, the bending of light that lets lenses focus starlight and makes straws look bent in a glass. But once light exits the material, it instantly resumes its full speed. This ability to slow down and speed up is crucial. Scientists wondered, if we can slow light with glass, can we slow it even more? Could we stop it altogether? The dance between light and matter is everywhere, shaping the world we see. Each interaction is temporary, but it hints at deeper possibilities. What if we could control light's speed completely? That question led to some of the most astonishing experiments in physics. In 1999, physicist Lena Howe's team at Harvard did the unthinkable. They slowed light to bicycle speed, just 61 kilometers per hour. They used a Bose-Einstein condensate, a supercold cloud of sodium atoms acting as a single quantum entity. In this strange state, a pulse of light crawled through the cloud, slowed by a factor of nearly 18 million. But they went further. In 2001, they stopped light entirely. A pulse entered the condensate, then vanished, its information imprinted on the atoms, frozen in place. Later, they revived the light, releasing it perfectly intact. This wasn't just slowing light, it was storing and retrieving it. Light, once thought untouchable, could be captured and set free. This breakthrough opened a new era, manipulating the very essence of light. It showed that information carried by light can be paused, held, and released on command. The implications for quantum technology are profound. We now had a way to control light's journey through time. While some scientists stopped light, others made it appear to travel faster than light. In 2000, a Princeton team sent a laser pulse through cesium atoms and saw the pulse's peak exit before it finished entering. Did this break Einstein's rules? Not quite. The trick lies in the difference between phase velocity, group velocity, and wavefront velocity. The group velocity, the speed of the pulse's shape, can exceed c due to how the medium reshapes the pulse. But the true information, carried by the wavefront, never travels faster than light. No causality was violated, no messages sent to the past. It's like a pattern of lights turning on in sequence. The pattern can move faster than any single bulb. This experiment revealed the subtlety of light's interaction with matter. The cosmic speed limit remains unbroken, but the possibilities are stranger than we thought. Light's journey through space and time is more complex than a simple race. To grasp light's weirdness, let's revisit the double-slit experiment. Fire photons at 2 slits. With both open, you get an interference pattern, proof that each photon acts as both particle and wave. Observe which slit it takes, and the pattern vanishes. Reality collapses into certainty. This experiment defines quantum duality. Reality is uncertain until measured. But what if we made slits in time, not space? In 2023, physicists at Imperial College London tried just that, testing if light could interfere with itself across different moments. Could a photon pass through two instants at once, creating interference in time? The experiment was designed to push the boundaries of our understanding of light and time. Creating time slits required a material that could change instantly. Enter indium tin oxide, used in smartphone screens. Normally transparent, it becomes a mirror for a few femtoseconds when hit by a laser. This fleeting reflectivity is a slit in time. Researchers fired a continuous laser at the material, then zapped it twice, creating two brief time slits. Each slit reflected a pulse of light, separated by a tiny gap in time. Classical intuition says you'd see two separate pulses. But in the quantum world, things get weird. The team looked for interference, not in space, but in the light's frequency. If the pulses interacted, they'd see a unique spectral fingerprint. The question, could light born at different moments communicate across time? The answer would reveal if quantum interference could stretch across the past and future. The results were stunning. Two time slits produced a complex interference pattern in the light's spectrum. Certain frequencies were amplified, others cancelled, forming peaks and troughs, a temporal version of the classic double-slit bands. For this to happen, waves from both slits had to overlap and interact, even though they were created at different times. It's as if the first pulse reached forward in time to meet the second. Quantum mechanics suggests light explores all possible paths, not just through space, but through time. Some paths are direct, others are exotic, involving faster than light or even backward in time journeys. The photon's wave of possibility spreads through space-time, probing every option before collapsing into reality. We never see a photon travel backward in time, but the interference pattern is proof that, in some sense, it considered every route. This experiment hints that light's journey is a quantum dance across the timeline itself. The boundaries of causality are more flexible than we ever imagined. Picture a space-time diagram, space on one axis, time on the other. Light's path is a 45-degree line, the boundary of causality. The time-slit experiment forces us to consider forbidden paths, faster than light, even backward in time. The observed interference pattern is evidence that light's quantum wave function explores these non-causal routes. It's as if photons send out feelers, probing both future and past. But we never detect a photon arriving before it's sent. This doesn't allow time travel or changing the past. Causality is preserved, yet it suggests reality is non-local in time. A photon's state may be influenced by its potential future and past. Time, for light, is an ocean of possibilities, not a one-way river. The light from distant stars has, in a quantum sense, tasted every possible route to reach us. Our linear experience of time is just one thread in a much stranger tapestry. Light's journey is a quantum exploration of all that could be. So, can light travel back in time? Not in the way we imagine. The 2023 time-slit experiment shows that, to explain what we see, we must accept that light explores paths unconstrained by our usual arrow of time. The interference pattern is a message from a hidden quantum realm where past, present, and future are deeply connected. This challenges our perception of reality and the principle of least time. The universe considers every possible path, no matter how bizarre, before settling on what we observe. These discoveries open doors for new technology, sensors, optical computing, and quantum exploration. We're learning to sculpt reality on femtosecond timescales, becoming active participants in the quantum dance. The story of light is our story of discovery, revealing a universe stranger and more wonderful at every step. We are stardust, briefly aware, gazing at the cosmos with light that whispers secrets of a reality where time is not what it seems. The journey of light is the journey to understanding ourselves and the universe.